So hoping that you can all see my screen right now. So here's my name. For those of you who don't know, if you don't know the year, here it is. If you don't know where you are, there's where you are. And my topic today is talking about object-oriented programming. And what I'd like to do is build it up from scratch several times in a row with the idea if we work in Python every day, everything around us is objects, but like a fish swimming in water, you're not conscious of the water. So I'd like to take us back to first principles and give you several fresh perspectives. If you've seen one of them before, I'm hoping that one of the other ones will be completely fresh for you. So I have a whole series of mini adventures for you, about a total of about 5 of them. And the 5th one is time allowing. So let's start on the first one. So the tools that we're about to need is namespaces. And namespaces can be implemented in several ways in Python. And one of them is with a dictionary. And so we make an empty dictionary, and I can store in there Raymond is red, and then do a lookup in that dictionary. And this thing is taking my keyboard away from me. We will see how well that continues to work as I type. All right, so we've got in a lookup. That is one way to do a namespace, but there's another as well. And that is whenever you save a variable, it's being saved somewhere. And the question is, where is that somewhere? The answer is it's also in a dictionary called globals. And so it turns out, whether you think you're using a namespace or not, whenever you save a variable, you're always using some namespace. So it's part of our world in Python to always have namespaces with us. In fact, if I update the globals directly, I can see a change in the variable. One thing that we don't really like about how dictionaries and work is that we have to use the square brackets and we have to use the quotes in order to do a lookup. And that can be a little uncomfortable. For globals, our speed up is we don't need the square brackets at all. We just type the X and the value comes right out. But there is another way as well, and it's in types. Okay. And it's called simple namespace. And so a simple namespace is a wonderful thing. It is just a data holder like a dictionary, where I said a X is equal to 99 and a Y equal to 100. And if I take a look at this namespace, how is that possible? It is possible because I didn't type the S. There we go. Never talk and type at the same time, just saying. All right, so the namespace looks just like the object that I created, although it's funny that when it prints out, it says namespace instead of simple namespace. And unlike a dictionary where you have to use square brackets to access all of the fields, you can use a dot. So dot X and dot Y. In fact, the reason that people like simple namespace instead of dictionaries is so that they don't have to use the square brackets and the quotes. So I've shown you 3 different namespaces, ones that you can make with a dictionary, ones that is just globals, and one that is in types, which is a simple namespace. And they all have different ways of accessing them. The way of accessing a dictionary was D square brackets X. But in globals, you don't need any of that. You just type X and it looks it up in globals. And with the simple namespace, it is namespace.x. So 3 different ways to do a namespace, and those are the tools that we're going to need. So I have a small project to work on, which is I'd like to emulate how dictionaries work. Okay. And a way to do that is to make a small hash table of size 8, and we can store all of the keys in an array of a list. for I in range 8 or range n, and we can create several buckets. Likewise, I can do the same with a value array. When I do that, I have three things in memory. I have a size, I have a group of 8 buckets, and 8 places for values. So suppose I have a key value pair where the key is Raymond and the value is red. The way you can insert into this dictionary is you need to choose one of the buckets according to a hash function, which is quite easy to do. We compute a hash of a key modulo the size of the dictionary. That gives us a bucket number somewhere between 0 and 8. So you go into the key array, look up the ith bucket and append to it the key. And do the same thing for the value array to store the value. This is an emulation of how dictionaries really work. The actual one in CPython uses very close to this technique, except instead of chaining, it uses open addressing. If you're interested in that, I have a separate talk on that subject that has been very popular. So I'll send a link to you for those of you who are interested. And this is how we say things in a dictionary. So here's the way I've been working. The project is emulate how dictionaries work. The variables are in the key array and the value array. And the place namespace where they're stored is globals. And my execution technique is manually typing commands. So we'd like to move up and improve this a little bit and make our project better. The first improvement is to move the operations into functions. And for that, I've already put one together for you where I just moved it inside a function. And this is a dictionary emulation using just functions. We've got a lot of screen space here, so I could probably make my type size a little larger for you. Do that momentarily. And you can take a look at the code on the right. So let me see if we can make this a little bit bigger. And, this talk is going to have a lot of code in it and a lot of live demos. Okay. All right, so the first thing we've got is setup. And what setup does is create our variables. And you can see where they're stored as global variables. Now, whenever we do a store operation, a store does exactly the operations I just showed you. So after 3 stores down here, the contents of the array are, we have in, the key array, and the value array. And the positions of these are determined by the hash function. I can continue to star other people. Bob likes green, and we can see where that goes in the array. So this is a nice improvement. The other tool is lookup. And lookup will look up one of these variables, and we'll look up Raymond. And that goes directly to the Raymond cell and pulls out the red without looking at the others. And this is what gives dictionaries their super fast performance. But if I look up Omna, we will get a key error. So our improvement here is that we were working in functions. So our project is emulate how dictionaries work. These are our variables, and the place where those variables are being stored is in globals. And our execution technique is now a little bit better. We have moved things into functions. But we have a limitation, and the limitation is this. In globals, are in one namespace, a variable name can be used only once. Okay, so we've already used in, K array, and V array. So our problem is in one namespace, we can use these variables only once, which means even though we have these three functions, we can only have one dictionary, and all of its variables are stored in globals, which is actually a terrible place for them. So here's the engineering problem. The engineering problem is quite simple. One namespace is not good enough. If one namespace is not good enough, what do we need? You can tell me in the chat window. Talk to me. I am feeling all alone here. If you all chat me up, I like to have two-way conversations with you while we're going along. And that's the correct answer is we need more namespaces. So we've only got one globals namespace, we'll need another. And a way to make those is using dictionaries. So our next improvement is to rewrite the code, this time passing in a namespace. And the namespace will be a dictionary. And so to store in, instead of just saying n equal 8, we store it in a namespace instead of globals. And the same thing for the K array and the var array. Otherwise, these functions are exactly the same as before. And our new approach is to emulate how dictionaries work with the same variables, but the namespace will be user dictionaries. Okay. Our execution technique is functions, and the benefit of doing it this way is we can have multiple namespaces, which means multiple dictionaries. So in namespace 1 is a dictionary, and my functions have been modified. The first argument is we pass in the namespace, which is just a dictionary. And if I need to look up a variable, I find it in the namespace. And if I store it, put it in the namespace. We say that namespaces are how the functions communicate. So when I execute this, namespace 1 is the first dictionary. Okay, and it has the K array and the value array, and it has colors, Raymond red, Rachel blue, and Matthew is yellow. But we also have a second namespace that has the same variable names, but this time we're storing a second dictionary. There's a different V array. I have a Mac, Rachel has a PC, and Matthew has a Chromebook. Interestingly, we don't have to pass in our own dictionaries. We can also pass in globals. So namespace 3 happens to also be globals. A lot of things will come out here, the other global variables. And what that means is everything in namespace 3 can be looked up directly, like the n and the key array, or we could say namespace 3 n and key array, and it would work. So this technique is very flexible. You can pass in your own dictionaries, or you can use the built-in globals dictionaries. Our big advantage here is we can now have 3 different emulations. If one namespace is good, 3 is better. And our technique is we make the namespace manually, and then we pass it in as the first argument to each of these functions. And this is a generally useful technique, and I hope you all learned something new. However, there's a problem. Writing ns v array every time I want to get to v array, well, that looks ugly. And are we happy with that? No, because the Zen of Python tells us differently. The Zen of Python tells us that beautiful is better than ugly. So we'd like to have something prettier than this. And so if the problem is namespace v array is ugly, the solution is somewhat obvious. The solution is simple namespaces, which I showed you a little bit earlier. So let's improve this one more time. This is exactly the same code as before, but this time, so we say simple namespace. And with a simple namespace, instead of writing something like ns var, which is unattractive, we can change it to something that looks pretty, like ns varray. Okay. So this looks really nice. It says go to a particular namespace and find the n in that namespace in the varray. And remember, the reason we have multiple namespaces is so that we can have several instances. This code looks prettier than before and more natural. And the way we use it is make a simple namespace and pass it in as the first argument. All the code here at the bottom is the same. So I can do a lookup in namespace 1 for Matthew and find that his color is yellow, and look up namespace 2 and find that he has a Chromebook. So 2 different instances. This time when we look at the namespaces, they're going to look a little prettier than before. It says namespace and it has the key value pairs. Otherwise, it looks amazingly like the dictionary. However, there's a problem, something we don't like. The problem is every new case, we have to manually create a new simple namespace. That is this part right here, this line and this line. That's no fun. But worse, we have another problem. Every single call to the function has to manually pass in the namespace for us. There's a solution to that problem, and the solution is Python's object-oriented programming, Python classes. And so we'll move up to dictionary version 4. This one is class-based. It's exactly the same code as we just had. There's a different, except all of this on the right has been indented on the left. And also, I've renamed namespace. Namespace is too obvious of a name. I need something much more mysterious. And nothing is more mysterious than calling it self. Self is the namespace. What does the class do for us? When we call dict, it builds the namespace for us. Every instance has its own dictionary. The other thing it does for us is instead of having to pass in the namespace as the first argument manually, the dot does that for us. So when we say D1 store, what it does is it passes the D1 in as the first argument, the namespace. Viewed in this way, you can see that all a class is a beautification of what we have already made here. Otherwise, the logic here is exactly the same. So this is fantastic. And we now have a class that works the same way as our other functions in multiple namespace. It probably doesn't surprise you, though, that there's a problem. And the problem is this. I have to type d.lookup, d1.lookup for Matthew. And it would work better if I spell it correctly. And that is unpleasant to have to type this method name. Likewise, if I want to do a store, I would have to say d1.store Matthew and give him a new color, orange. It is no fun to have to type this. Our problem is the method names are too hard to type. The solution is operators is change the method names so we can use operators. And it's a very simple thing. This will be exactly the same code, predict class, predict magic rather, that's number 5. And this one looks exactly like the code on the right, except setup now has a name, dunder init. Store is now called dunder set item, and lookup is now called dunder get item. The advantage of those name changes is instead of having to call setup separately, it gets called automatically. And instead of having to say store, we can use square brackets. Instead of saying lookup, we can also use square brackets. And what I've showed you on this journey is that object-oriented programming is not particularly magical. It's the idea that one namespace is not good enough. Therefore, we want multiple ones. We need to pass in the namespaces to the functions. And the most beautiful way to do that is to put it in a class and to have the operators call the methods for you. But there's nothing magical here. These are things that we would have done anyway without object-oriented programming. In fact, before object-oriented programming, it was very common to pass namespaces or environments or context into objects. I hope you saw that got a fresh perspective on object-oriented programming, and that is adventure number 1. With that in place, let's go do adventure number 2. I'm going to tell the object-oriented programming story again in a completely different way. A long time ago, in a galaxy far, far away, it was 1980. And in 1980, there was a software crisis. Lots of people knew how to program computers. We had a lot of computers. We had some big projects. And in the 80s, almost every major software project in the entire world was a failure. Not all of them, but almost every single one failed to some extent. And this was called the software crisis of the 80s and the early 90s. I'd like to take you through that crisis and give you a solution to the problem. Once upon a time, we had a big pile of stuff called data that we gave variable names. If these variable names seem terrible to you, it's actually how we used to name things. A, A1, A2, B, C, D. Short variable names were very common back then. So A was an integer, B was a list, which we called a vector. There is a two-dimensional array, another two-dimensional array that's square, a string, a file, a Unicode, an open URL, and so lots of different kinds of things. One big steaming pile of data. But we didn't just have data, we had something else. We had functions that we could call on that data. And these functions include closing a file, computing a vector cross product, a dot product, eigenvalues of a square matrix, matrix inverse, matrix multiplication, the size of a matrix, multiply two numbers, read a file, get the length of a string, write to a file, get the length of a Unicode string, uppercase a Unicode string, uppercase a regular string, read a URL, get the size of a vector, and write to a file. A big pile of functions. And all of these things existed in one namespace. And if you detected the theme of the talk already, one namespace is bad. How bad? Our problem was this. Whenever you wanted to call a function with the data, you had to know which one. There's only about, a dozen pieces of data and a dozen functions. But 12 times 12 is the n squared problem. There are 144 possible connections between these things on the left and the right. And the way we used to write our code is in the form verb, noun, noun, which the verb is multiply, and the nouns were multiply A and C together. And matrix multiply, the matrix E times the matrix F. And this was life during the 1980s. And it was terrible. Did I mention there was a crisis? Yes, everything was falling apart. What was the problem with what we were trying to do here? There were actually 4 major problems. One problem is knowing which function went with which piece of data. And if you ever called the wrong function with the wrong data, you got the wrong answer. For this amount of data and this number of functions, that's not really a problem. But when you get up into thousands of functions and thousands of pieces of data, a very common source of failure is a person would call the wrong function with the wrong data. More than once, we lost a probe on the way to Mars for exactly that problem. The AT&T telephone network went offline for 8 hours for one day for exactly this problem. It doesn't seem hard until you've got a lot of functions and a lot of data, and it's an n-squared relationship between the two. Another problem is these functions are not well organized. There is no organizing principle. One thing that we can do is some type checking to know which functions go. The problem is, let's say you have a function pow. Pow 2 to the 5th and 5 squared are not equal to each other, but to a type checker, they are both integer to integer maps to integer. And that tells you that a type checker can help you a little bit, but it can't make sure that you get all of the pieces of data correct. Your program can still be wrong and still be type correct. There's no way to introspect this object and ask it questions. What kind of object are you, and know how to do. And the learnability problem was terrible. If you started work at Bell Labs, they gave you a stack of books 3 feet high and gave you 6 months to read them. And you learned all 5,000 of their functions before you could do anything useful. It was a terrible learning process. 6 months before you wrote your first line of code. A lot of risk, call the wrong function with the wrong data, knock the network offline, type checking didn't help you, no introspection. This was a terrible time. So let's go fix it. The big idea was objects. And what is an object? The data is directly associated with the functions that operate on that data. So in addition, we store A as 5, but in addition, we say the functions that are allowed to work on that are the 5 can be multiplied or get the absolute value. Or this vector, the 3 things that can be done on it is a dot product, a vector link, and a cross product. Now every piece of data has a list of all the functions that work on that data. This is a huge win, but it changed the way we wrote code. Instead of verb noun noun, it is now noun dot verb noun. We would say object A, integer A dot mul C, dot matrix E dot mimmul is times E transpose, and matrix F is M size, or hello dot upper, which probably seems very familiar to you. So what is the notion of an object? Every piece of data knows the functions that are allowed to work on it. What are the benefits here? One of the big benefits is it's no longer possible to call the wrong function. If you have A and you call dot product on it, it will know right away that's the wrong function and give you an error. Whereas previously, it might have segfaulted the entire system. So we have solved the problem of calling wrong function with the wrong data. Also, we have introspection. If you get a job and you're told, go do something on F, you can do a dir listing on F and it lists out all the things it knows how to do. You don't have to learn all 5,000 functions before you do anything useful. That's where at places like Dropbox and Facebook, that's how it's possible that people are able to contribute a line of code in their first week at work. And that's solely because of the object-oriented programming. So this is a major improvement. However, there are problems, as there so often are in my talk. And the one problem, and I'm losing my screen here, is we have repeated this list of functions, mul and abs, multiple times. We've repeated this one multiple times as well, and this one is multiple times. And so this eats memory like crazy. If every function, it takes, every piece of data has a very long list of functions. So it eats memory like crazy because of redundancy. Also, we don't have any way to describe this group of functions. It doesn't have a name. That problem is, of course, easily solved. After the invention of the object, the next important thing was a class. And yes, it's true. You can have objects without classes. But what are classes? Classes are just those groups of functions that you create exactly one time and you refer to them by name. So for A, we store exactly 2 things, the number 5 and that its class is a scalar. We store 2 things for B, the list and that it is a vector 3. One cool thing about this is we're now giving this names, and I can have standard names for these. These are a str, this is a file, and this is Unicode. But what are these names? They are references to the list of functions. So when you say a.mul, what it does is it says a is a scalar, looks up scalar, and finds mul and says that's an allowed operation. This is great. It takes a lot less memory than it took before to repeat these lists over and over again. We have the list exactly once. And our other benefit is we've given the concepts names, and we can now say, go use all of the square matrix operations, and here's the values allowed for a square matrix. You probably suspected there's going to be problems. And there is a problem here, and that is this vector supports dot and vlen, but a vector of length 3 also supports cross product. You'll notice that this group is contained in this one. The subgroups are in this. So there is repetition that is unnecessary over here. In addition, we haven't expressed any relationship between any of these. The solution to this is very straightforward. We call it inheritance. What is inheritance? Inheritance says, what does vector 3 do? It says it does everything that vector does, plus it adds a cross product. And you might say vector 3 is a kind of vector that has a cross product defined. What about a square matrix? A square matrix can do everything a matrix can do, but it can also have a inverse, and we can compute eigenvalues for the matrix. One win here is that we have many fewer functions on the right, far less redundancy. This improves code reuse. Another thing is that we've given names to these relationships, and we can express structures of ideas that previously people kept in their head, but they didn't have a good vocabulary for. And our calls for this are the same as before. We've got G, the string, get its string length, and D, the vector length, and then F, the matrix size. But there's something that we don't like about this. All three of these things have the same concept, the size of the object. This one is the size of a string, this is the size of a vector, and this is the size of a matrix. They are three different functions, but they have the same concept. And it overloads the mind to have to remember all of these names. But it's not just the mind that's a problem. Sure, you have to remember all of the names, but there's an even bigger problem, a horrific problem that was characteristic of almost all of the languages of the 1980s. What we used to have is big case statements. You're looping over a bunch of objects, and you say, if it's a matrix, print the matrix size. If it's a vector, call the vector len, and if it's a string, get the string len. And that way, we can get the size of all of these objects. It was very common in the 80s and 90s to have code where 90% of the code was a big pile of case statements. If it's a long-term life insurance policy, if it's a short-term, if it's a whole life insurance policy, if it's a term life with an annuity, and each case had its own function. And this, writing code like this would destroy your soul. It would eat you alive and make you want to become a flight attendant rather than a programmer. This was terrible. So we needed a new invention. And the new invention was just a naming convention. It's called polymorphism. And polymorphism just means we use the same name for different functions in different classes. So instead of calling it vector len, we call it len. And instead of calling it string len, we call it len. And instead of calling it Unicode len, it gets called len. Now, when you're learning an object-oriented language, you don't need to learn a lot of concepts. You can learn very few concepts. The learning curve went way down. And look at the calls now. Glen, hlen, and flen. These are three different functions. And these two multiplications, this one's a matrix multiplication, and this one is a regular multiplication, and they all look the same. Not only is it less of a burden on your mind, that really nasty chain of ifs and elifs we saw before is now gone, and our for loop looks like this. Loop over all these different types and call len on it. Polymorphism isn't something cute. It will save your soul from destruction. If you ever find yourself writing big if chains or case statements in the language, you'll say, hey, we solved this problem a long time ago with polymorphism. And that takes us to modern times, and that shows you another way to look at object-oriented programming. What is object-oriented programming? It is a solution, a direct solution to a long series of problems that we had over and over again. We really did use to code like this. It was common for a scientific company to have a library of 5,000 functions. I remember as a kid seeing giant tables full of books where the functions are indexed alphabetically and a person would have to look up the function. If you updated it, you gave it to a secretary to type it, and then what they would do is pull out the old page and stick it in the book. And all of the documentation was in the computer. This was a terrible way to program. If you're ever given a language that looks like this, you should run and say, that's so 1980s. And object-oriented programming solves these problems for you. It's not a perfect solution for everything, but it's a direct solution to real problems. And that is our second adventure in inventing object-oriented programming from scratch. I'd like to do one more adventure, which is to show you something in the collections module called a chain map. And that is something that I created. So let me show you how the chain map works. It's actually a very simple thing. My screen is rather busy, so let me clean it off. And we'll say from collections, import star. And a chain map is a very simple thing. It takes multiple dictionaries and it connects them together. I have a dictionary A is 1, B is 2, and I chain it together with B is 3, and C is 4. What it does is it takes multiple dictionaries and it gives you a single view of the dictionary chain. So D square brackets A searches the chain and finds the A is 1. DB, it finds the very first one in the chain, scanning left to right, and it returns the B is 2. We say that this one gets shadowed. But DC doesn't find it in the first dictionary, and it goes out to the next one. And then DD doesn't find it at all, and that view raises a key error that it's missing. It's called a chain map because it chains several dictionaries together. So let's look at Python's object-oriented programming. We have a class P, and in P is a namespace, p.x, p.y, and p.z are these three class variables. We have another class, c.y and z are these two numbers. I have instances of that class, and in the instance, a.z has been stored in the instance namespace, and b.z has also been stored in the instance namespace. Which raises the question, how do all of these things relate together? And it works like this. For A, if I type in Z, these Z's get shadowed by the instance. If I put in A.Y, it works its way up from the instance to the class and finds the 444, and A.Z, or A.X rather, works its way from the instance all the way back up to the parent. B has a different namespace, so B.Z is different, but otherwise, its parent classes still give the same answer for Y and X. And that is basic object-oriented programming in Python. What I'd like to show you is that it's actually a very natural concept. Python object-oriented programming is just a chain map. I'll take the variables of A. So here's the instance dictionary for A, and the variables for C. That's the things that we stored in C, and we chain them together. So now I'd like to show you that the chain map is isomorphic, meaning identically structured to these data. So the instance A, we have A.Z. But in the chain map, if I look up Z, I get the same thing. If I look up A.Y, the chain map gives the same thing. And if I look up A.X, the chain map gives the same thing. The second one has a different element at the beginning of the chain, B. And so B.Z gives the same thing as MB, Z. B.Y is the same as the chain map for Y and X. And this concludes your third adventure in object-oriented programming. What I've shown is if you have a language with dictionaries and you can chain them together, object-oriented programming happens naturally. It says, look in this namespace, look in this namespace, look in this namespace. We do this in the real world all the time. You go to the branch library looking for a book, and if you find it, you check out the book. But if you don't, you put in a request and it goes to the main library and they give you the book. But if they don't have it, they put in a request to another university's library and they pull the book from there. There are several different namespaces, your local library, the main library, and then the chain of other libraries. That's a chain of namespace. And if you've ever borrowed a book, you've used object-oriented programming. That is your third adventure of building up object-oriented programming from scratch. And I'm hoping each one of these gives you a completely different perspective. Another thing I'd like to show you is that it arises naturally from entity modeling. So when you're describing data, object-oriented programming just happens. So let me see if I can organize myself here and find that quickly. We got Aquamax. There we go. All right. There is a programming language called Bloop. Those of you who've seen the book Gödel, Escher, Bach have seen this language before. This defines a procedure, factorial, and it's a block structured language. It defines an initial output, a cell value, fixed length loops, multiplies an output times a cell and adds one. And this is a procedure in that language to compute a factorial. Now, what I'd like to do is parse that language. So I wrote a compiler for it called the Bloop compiler. And the Bloop compiler, what it does is, let me give you the, I'd like to show you that one parsed. In fact, Bloop, AST Bloop. One Bloop short right now. Here we go. The AST for the Bloop. There you go. What abstract syntax tree is in a compiler is an analysis of this code. And it creates an object tree. And it says the whole thing is a program that consists of procedures. The first procedure, its name is factorial. It has a parameter in, and it's not a test. It has a block of code, and the first thing it does is an assignment to this output name, which is not a Boolean, and the value of it is 1. This is a step in compilation. If you can transform something like this into something like this, you have written half of your compiler. So this is an abstract syntax tree, and these things are descriptions of the entities that occur along the way. Which raises the question, where do these names come from? How do you describe a program? When you start describing a program, concepts come up and they have a relationship to each other. And it turns out the most natural way to model that is through object-oriented programming. You can write regular classes for it, but it's also easy to use either data classes or name tuples, which is what I did. So the abstract syntax tree is described in a language called ASDL. And it says every program consists of statement procedures and some calls. Statements are either a procedure, a block, assignment, a conditional, a loop, an abort, or quit. And expressions include binary operators, numbers, booleans, ID identifiers, and calls and L values. And then we have a definition of L value. This is the structure of the knowledge. It emerges from studying the programming language. When you study a language, its inner bones, our skeleton of structure, is described, something like that. But now we want to represent that in Python. And it turns out this translates very naturally to classes. And so I was able to describe it quite easily. A class program is a name tuple, which has procedures, which is a list of statements, and calls, which is a list of expressions. What is a procedure? Well, every procedure has an identifier, a list of parameters, an indication of whether it's a Boolean or whether it's a test or whether it returns a number, and then it has a body with a bunch of statements. So what we just saw, that output on the previous screen, was really a nest of all of these things. The point here being, whenever you're studying something complex, like an entire programming language, there is some inner structure. And when you start to describe that structure, you end up inventing new words and relationships between these. These are called entity relations, or ER diagrams. And it turns out the most natural way to express them is in terms of classes that contain other classes. Here we're using modern type annotations along with the names. And because I use name tuples, my building all of these classes took about 5 minutes. In fact, the only hard part was analyzing the language. Once I had analyzed the language, implementing it was just a matter of minutes. Once you have these classes, it becomes very easy to loop over all of the children and display all of the nodes. The other bit of modeling that I wanted to show you is I've invented my own version of Twitter. Okay, so you've got real Twitter right here. And what's in it? You have people's posts, you have a picture, you have a summary, and usernames. Twitter is obviously a very complex website, which raises the question, how difficult is it to model in Python? Well, I went to build my own version of Twitter. And let's see if I can find which screen it's on. And I've got it up running on a server right now. Let's turn back to our let's really seize control of my computer. So I need that link though. So this is currently running on my computer. It's my version of Twitter, which I call Messenger. You could search for Python on it without logging in, and it'll give you people's tweets or messages. Or if you log in, it'll give you more. And you could go in and see my friend Davin, who has posted 3 times. He's following 2 people, me and Barry Warsaw. And he has 1 follower, my favorite data scientist and friend, Michael Selleck. We can also search for particular topics, or we can find out what Davin has to say. And Davin's the person who taught me that coriander and cilantro come from the same plant. So how difficult would that be to model in Python? And the answer is not difficult at all. I'd like to show you, through the power of object-oriented programming, how all of that is modeled. And if you all want a link, I can give you all of the source code for that entire program. The back end is about 100 lines, the front end is about 100 lines, and the HTML is about 100 lines, so a very short program. A user is represented by a string. A timestamp is a float. A user's hash is a tuple of bytes and some more bytes for assault. A hashtag is a string. A post, something you call a tweet, is a name tuple, and every tweet has 3 parts: a timestamp, when it was tweeted, the user who tweeted it, and the text of their tweet, 140 or 280 characters. In addition, we have info on users. Every user has a display name, email, we've stored their hash password, and they have an optional string biography and an optional, this is a string for the photo, so it's a file name. And the data structures we store them in is every post is stored in a deck arranged newest to oldest. We also store it in a default deck so that we can look up, let's say, all of Donald Trump's posts and find them newest to oldest. And it looks like I'm coming up on my Q&A time here in just a moment, so let me wrap it up really quickly. Hashtag index is also a dict so that you can look up a hashtag and find every post for that hashtag. Following is a default dict of set where you look up one user and you find the set of everyone they're following. Likewise, followers is a default dict where you look up a user and you find everyone they're following. And then there's a regular dictionary where you look up a user and you find their info. This one page describes all of Twitter. You should be dazzled and amazed by that. This is the power of object-oriented programming. It naturally expresses entities and relationships. And that completes our 4th adventure of reinventing object-oriented programming from scratch, from solving the original function problem to applying namespaces, the chain map point of view, or it falls out naturally from entity relationship modeling. It turns out there are many, many problems in computer science, and many of those paths end up at object-oriented programming, much as we've implemented in Python. I hope you've enjoyed this talk. I'd like to open it up for questions, and I'm hoping that someday you invite me to visit Estonia in person. I would love to see your country.
Thank you so much, Raymond. It was an excellent talk, a lot to learn, and we can actually start off with the questions and answers. So you can either send in your Q&A, or I guess all of you are unmuted if anyone just wants to ask a question. Go ahead.
Okay, is there something I should be looking at so I can see their questions? I've got a chat window up, but I don't see anything.
Nobody has written yet anything in the chat, but they can if they want. They're also unmuted, so if they want, they can just.
Okay, good enough. Well, anyone ask me anything?
Jaa, kui veel. Mart, jah.
Amna, is there a chance that you could grab a question for me and repeat it for me so I can answer, because I'm not making out anything?
Yes, there's one question about what are your thoughts on functional programming?
I love functional programming. I think it's awesome. I wrote the itertools module because I love functional programming so much. That said, functional programming doesn't work nearly as well for these problems. Functional programming is not good in modeling all of Twitter like a pile of objects are. Functional programming is not particularly good at managing a series of namespaces like we did in the dictionary object to begin with. It can do it, but it's not its forte. So I use functional programming for things functional programming is good at. I use object-oriented programming for things objects are good at. And the two actually mix and match pretty well. For instance, in the code that you can see on the screen, when we want to find all of the posts for a user, everyone that Davin should see, it's only 2 lines of code because that code is functional programming. So we look up in our data structure, the user Davin, and find everybody that he's following. And we loop over those and we find in user post, the post for every person that Davin's following. Then we run a merge on that. And that builds a iterator that merges the post newest to oldest. Then the functional tool iSlice will pull off, let's say, the first 10 posts, and this turns it into a list. This is fast, It's efficient and it's clean because of functional programming. So more about functional programming should be in another talk, but I think the two techniques blend together very well. When I'm processing data, I use functional programming. While I'm laying out and managing state, I use object, and the two fit together perfectly. Great question. Next.
There's another one about what you think is the best way to apply this for a small SME.
What do you mean by SME?
I would let the person who has asked the question, I think it's Carl, want to also small and medium enterprise.
Oh, I see. When I was very young, I learned the programming language BASIC. And the first example I gave you in the software crisis came from the kind of code I wrote in BASIC. When I said that we had these function and data, this is what my BASIC code looked like. And BASIC was great because it was easy, but it was a problem because there was only one namespace. It didn't scale. So I had no problem writing 50-line programs that played Lunar Lander or a Star Trek game. But if I ever tried to do something serious, the language would fall apart very quickly. Now keep in mind, modern versions of BASIC do have objects and they do have namespaces. But the version of BASIC I had didn't have any of these things. And so my problem was, even though I was a decent programmer, the tooling I have, it couldn't scale and I couldn't solve any interesting problems. So I would say to you, object-oriented programming is there to help you manage the scale that you have at a small to medium enterprise. That in fact, programming without objects, with just a big pile of functions and data, reinvents all the problems we used to have, and it was a disaster for small and medium businesses. So this actually is a solution to your problem. It is a technique for managing complexity, which is something that you want. One other aspect of object-oriented programming we didn't talk about was encapsulation. And the idea is people are giving you objects fully formed. So as a small and medium enterprise, you don't have to write all the code yourself. You download a package from the Python package index. It has some objects in it. You load the objects and run the methods on it, and you don't have to know anything about what's inside. And that's why it's possible for a small group of people, like 20 developers was all it took to make Instagram. 5 developers built the original version of Dropbox. The original version of YouTube was written by a team of size under 30. Object-oriented programming and pre-made packages made that possible. In other words, object-oriented programming is a gift to you in this time from your parents and grandparents from the 1980s and 1990s. They saved this up for you so that your success would be possible. Great question. Next.
There's a question, is method overloading a good thing?
The way you ask it, it sounds like it could be bad. I don't think so. The word overload is actually overloaded itself, and it's used in a couple different ways. Sometimes people mean it in the sense of C++, if I'm overloading an operator. And Python doesn't do that. Our operators are hardwired, plus is hardwired to dunder add. So instead of overloading the operator, we make a class that knows what to do with that operator when it's called. And that's a very good thing. It's why the core language has a plus that adds integers and strings, but extension packages like NumPy are possible that add arrays together. So the reason that Python is still significant in areas like data science is because of the equivalent of operator overload. But perhaps you meant where you have a parent class and a child class overrides one of the methods of its parent. And you're asking if that's good. And the answer is, sometimes you can't get away from it. The reason that we have inheritance is so that the subclass can reuse the parent's class methods. But sometimes the parent's methods don't make sense and you have to override them. So the good part of inheritance is you get code reuse. The bad part is sometimes you inherit methods you don't want. A solution to that problem, or a Band-Aid, is overloading it. However, when you use that Band-Aid, you get the good effect of a new and better method, but you get the bad effect of the child class isn't substitutable for the parent. So it's a trade-off, like many things in engineering. You're solving a problem as easily as you can, but almost all solutions to problems beget their own problems. I had a friend who went to pharmacy school, and when she graduated, she told me what she learned. And basically this, she said, every single drug we have is a drug because we know it solves some problem. However, every single prescription drug is a prescription drug for a reason. It's also bad for you in some way. Every single drug you can take has some negative effect. Otherwise, it wouldn't be a prescription drug. So she said the science of pharmacology basically boils down to look at what problems you have that are really important, take a drug and trade, solve a major problem in exchange for getting a more minor problem. Overloading methods is exactly like that. You're solving a big problem, inherited a method you didn't want, you're repairing it into do something useful, but you lose substitution. Another excellent question. Thanks for asking.
Yes, there's another one. What is your personally favorite part of Iter Tools module?
The combinatoric tools, that would be product, combinations, and permutations. When I wrote them, I had a mathematical interest in them, but I had no idea how powerful they would be. So when I'm writing tests, I take user events. A user can do step A, B, and C, but maybe they could do C first and then B and A. So I run all permutations of a thing a user can do. What if a user sends you money just before they close their account permanently, 2 days before you were about to ban them from a user, but their trial membership still had a few days left in it? What should the system do? Those tests are hard to think of, but permutations can generate all of those tests. Likewise, a product, every category of user with every category of action. I found an amazing number of ideas, particularly in testing, are very easily expressed with the combinatoric tools. They are my personal favorite. Thanks for asking.
Other questions are interesting. There's one, what is the best thing written in Python that you have seen and why?
I've seen a lot of good things in Python, so it's difficult to narrow down. But I think the first time I saw inside a microweb framework, I was dazzled and amazed at how clean the code was. So my personal favorite in terms of readability is Bottle. I know that Flask has become more popular, but Flask is rather large, big enough to where most people never read the source code. If you read the code for Bottle, and you can read it in about a day, it's about 3,000 lines of code, you will know completely how a microweb framework works, how templating works, and you'll realize it's astonishing what can be done with a small amount of code. So that is one of my favorite pieces, but I bet if I thought about it more, I'd find others. So if you want some weekend reading, the kind of weekend reading I do, download Bottle, B-O-T-T-L-E, and read the source code for it. It won't take very long, and it will make you smart. Next.
There's the best way to pass an object from one endpoint to somewhere else. What's the best way to pass an object from one endpoint to somewhere else?
As in between two different machines?
I guess, yes.
If you are passing it between processes or machines, you either have to destructure the object into components manually and then load it into a format like JSON for transport, or PyProtocol, so manually unpack it into a binary format. Those are pretty decent ways, but the easiest way is to use pickle. It's fashionable now for people to hate pickle for lots of different reasons, but it's really astonishingly good. Let me show you an example. I wrote this version of Twitter, and it is the entire backend for Twitter. The problem is it's all in memory and I can't share it between machines. Which raises the question, how much effort is it going to take all of the tweets and all the relationships between them and transport that between machines? The answer is down at the bottom is I save it by opening a pickle file and do pickle dumps, and it takes me one line of code to save the entire state of all of Twitter all at once. And it takes one line of code to restore all of that code. Pickle is really, really good at what it does. Now, you should never unpickle something that you don't trust. So if you're moving pickles around, you should probably sign them or only accept them from yourself. Don't accept them from outside parties. They do have some disadvantages, but what they do is astonishing, and that's how I move objects around. It's also how the multiprocessing module does it as well. And I believe PySpark uses a similar technique. Twisted has a variant on it. I think it's called Twisted Jelly, and there are a number of other tools. But Pickle is my favorite. It's supported directly by the language, and it's well tested. And even though a lot of people hate it, it's very, very good at what it does.
So next question is, what is your opinion on meta classes?
I love them. If they are taught to you properly, and I teach Python for a living, so I can, in a few hours, take people from kind of intermediate programmer to being able to handle descriptors and meta classes, and properly taught, you realize they're remarkably simple. Meta classes in many ways are no different from regular classes. They just have a different application. So I do like them. And one thing that never fails to astonish me whenever I am working with people in meta classes, helping them create them, is many classes we create are like the ones that I showed you today. They can be quite large. So classes can have dozens or hundreds of methods or be several hundred lines long. But many useful meta classes are 3 lines long or 5 lines long or 8 lines long. It doesn't take much to make a very useful meta class. And the kind of things that meta class does are often hard to get in other ways. That said, if people aren't thoughtful about how they write meta classes, they can easily create chaos if they're rearranging the internals of Python so it doesn't behave as people expect. So they are dangerous in that it's very easy to create atrocities that are difficult to debug. So if you use them for good things, they're great. But if you use them haphazardly, they can really create some serious misunderstandings, and that's given them a bad reputation. Another problem is that if you start to use meta classes everywhere, you'll find that you override exactly the same methods, and it's fine until you try and use 2 meta classes together. We do have techniques for solving that, and it's called cooperative classes, but it takes some skill to do that. And most people would rather just say, I hate meta classes and avoid them entirely. The thing is, if you don't use meta classes, you end up with a lot of substitutes like there are various hooks, like there's a new one, dunder init subclass, and that saves you from writing a meta class. Class decorators are an alternative. But all of these alternatives were created simply because people either didn't learn meta classes, were scared by them, or they got burned by them once. So do I like them? Yes. Does lots of great code rely on them? Sure. The Django ORM is not possible without a meta class. Python's abstract base classes created by Quito is not possible without meta classes. It is often the simplest way to get something done. So I'll summarize then with the Spider-Man rule. With great power comes great responsibility. Use meta classes for good, not for evil. They can tie you in knots, but they can also solve problems elegantly. So there you have it.
Great. I have one more question, but I would just take this as the last question. If there's someone who wants to ask a question by just unmuting themselves, we can go ahead with that question instead, or I would just read this out.
Why don't you just read yours? You're reading them so clearly and perfectly. I welcome your next one.
Okay, so someone's asked for recommendations for types of projects to work on that help with gaining a better understanding object-oriented programming.
I'm going to do a little evasive maneuver on that question in that I can't think of categories of projects that teach you more object-oriented programming. If I had to grab one right offhand, it would be what was done with the Twitter, this kind of project of modeling a website. So go out and model within a few lines of code, try and model Wikipedia or Craigslist or Facebook or some major service. And it should be that the core functionality should be something that you can model in one page. That's a reasonably good exercise. Also, if you build a compiler, and that is not an easy project, but if you go to build a compiler, that other example I gave you with the abstract syntax tree, that'll teach you a lot about object-oriented programming. But the evasive part of this is I'm not going to recommend projects to go to. Just solve real problems. Don't go do made up projects to learn it. A enhanced version of your question is, what is a good way to improve my skills in general? And I believe the best answer is read good code. So open up the collections module and read the code inside. You'll find some code written by Guido. You'll find some code written by me. Open up the Func Tools module and you'll find some code written by Wukash, for example, or myself or Nick Coughlin. And so learn from the people who are the best in the business. The standard library source code is easy to find. It is not necessarily the most beautiful, but there's a lot of good techniques in it. And that's the way I improve my skills. So every now and then I find a project and I download it and I just go read all of the code when it's written by somebody I admire. So I spent some time reading some of the source code for NumPy and I learned things that I didn't know. And I had recommended Bottle. Bottle is a one-day read. And at the end of that one day, you know a lot about objects. So grow your skills by reading excellent code. There's a couple books that will really help. One of them is called Refactoring. I think that is by Martin Fowler. And there's a couple of principles that you should look up. One of them is called the GRASP principles. Okay. Pick up Martin Fowler's book on refactoring. That will make you good at objects really quickly. So this will give you some of the theory, and you should learn some things like Liskov substitution principle. So learn some theory, but mostly go read code. And in great code, you'll hear people talking about single responsibility principle, for example, and refactoring, and Liskov substitution principle. There's another fairly important principle called the law of Demeter. And these will give you some rules of the game. The refactoring book, like I said, is just excellent. Its examples are in, I think, Java or C++. But it's very easy to write those examples in Python and learn from them. I spent a weekend with that book and it improved my skills immeasurably. So read good books, read the theoretical principles, read good code, and a little bit of heresy. Read something other than Python.
Perfect.
Python people don't have all of the answers. C++ people know some things too. Java people know things too. Smalltalk solved a lot of problems a long time ago. In fact, pick a language wildly different from what you know and just spend a day with it. If you spend one day with Forth, it will change your life forever in terms of how you program. If you spend one day with APL, you'll finish that day with a headache, but you'll walk away coding differently for the rest of your life. Haskell, you can't spend one day with. I wrestled with it for about a month before I was able to get my first programs up and running, but it was a mind into it. Prolog will grow your brain. So I would say learn different patterns of thought. But another way, if you want to grow, just don't get stuck in a rut. Otherwise, you'll find that you've done the same thing the same way your whole life and will have finished a long software career and not have learned a lot of things. So get out of your shell, go see new things, and go to conferences like this one and listen to people. That's my advice. Hope it's useful for you. Amna, thank you so much for inviting me. When this coronavirus is done, do I get to come see you all in person?
Yes, please. We would love that if you visit us. Who knows when? Maybe.
Yep. When it's all over, I would love an invitation to come see you in person. Thank you all. It's been an honor.
Thank you so much. Thank you for your time. Thank you everyone who was here. I'm getting in a lot of comments about how awesome the lecture was. Everyone really enjoyed